already some time that we forgot. I mean, we might have forgotten some of the things, and so I just want to recall some of the things. Okay, so we started with the Fourier series. Okay, and so I mean, you know the history. Let's not go back into the history. So we started with the Fourier series, and so we wanted to see. Okay, so we wanted to see whether it is possible for us, given a function, okay, that is going to be, periodic with some period. Okay, so for our simplicity sake, so we said that we are going to consider only 2 pi periodic functions. Okay, and then we wanted to try and see whether we can really write down f of x to be equal to summation a n cos n x plus b n sin n x. So we want to try and see whether we can possibly, I mean, so this equality we will have to really make sense once again. Yeah. Sorry. One second. Okay, so we wanted to try and see whether we can possibly do this, and so we just thought, okay, instead of writing down a n cos n x and b n sin n x, and because we have got these conditions, I mean, so we have this relation that cos n x equal to e to the I n x plus e to the minus I n x over 2, and then sin n x is equal to e to the I n x minus e to the minus I n x over 2i. So you want to use these two relations, and then so which means that we can write down f of x to be equal to summation minus infinity to plus infinity cn e to the I n x, where you may possibly have this cn to be complex numbers now. Okay, and so this is reasonable as f is 2 pi periodic, and so are e to the I n x for n in z. So both sides are going to be 2 pi periodic. So, well, if it is possible, if it is really possible that we can write down something like this, okay, under what conditions? This is something that we have to ask ourselves. Okay, and so naturally, once, if at all we can write down, we want to try and find out what are those CMs now. Okay, we have to know if there is a possibility to calculate these CMs. Okay, and then after that you will think about the convergence of this particular series, because this is now a sequence of series of functions now. So we want to try and see if it is possibly going to converge, if at all. Okay, converge uniformly. Only then you can think about a given function. Of course, pointwise convergence gives you a function, but the function may not have really very nice properties, because see, on one side, see, you can see on the right hand side everything is very smooth. These functions are all smooth functions, and so on the other side you want to try and find out if we can possibly get the function to be a nice, we may not be able to get everything possibly, but then we can get, under what conditions we can get that function f to be continuous, under what conditions it can be differentiable. All those things have to be found out. Okay, so but then even before that we need to know what is the series. If without that, I mean, without having these CNs explicitly, we will not be able to really understand the convergence at all. Okay, we cannot even discuss. But then see, this sequence of functions that you have got e to the I n x, n in z, have the following orthogonality property that you know already. Okay, integral minus pi to plus pi e to the I n x times e to the minus I m x. Sorry, this x is not looking like really x. I just want to change it, because I keep on asking you people to write down properly, so I would rather do it. Okay. So that, okay, so that's what it is. So now, well, this has got this property that e to the I n x times e to the minus I m x dx, which is integrated on the interval minus pi to plus pi, is going to be 0 if m and n both are not the same. But if n equal to m, then you have the value to be equal to 2 pi. Okay, but then let me tell you, this particular integral that you are looking at comes from actually the L2 inner product. It is called the L2 inner product. So whatever I have said here, the L2 inner product. So this is the L2 inner product that you have got. Okay, that is integral minus pi to plus pi f times g bar dx, that is the inner product that you have got. And if f equal to g, then this is just going to give you the norm square of f. Okay. And now, okay, so well, I wanted to find out what are CNs now, because because of this kind of orthogonality relationship that these functions satisfy. So I can always use this particular property to calculate my CN. What is the way that I would do? I would just hit it. I would just hit the sum that I have got. So what is the sum that I have got? This sum that I have got out here, I'm just going to hit it with e to the minus inx on both sides, because once I am, see, okay, all this and whatever I'm trying to do now, f of x equal to, so this equality should be taken with a pinch of salt. Oh, sorry. Okay, there are several people waiting in the waiting room. Sorry. Okay. Okay. Vijayan seemed to be having some problem. I don't know. Actually, I admitted him earlier on also. Can you please check whether Vijayan has come? Did he join? Vijayan?
He doesn't seem to be in the meeting room.
Yeah, but I mean, no, actually, I allowed him earlier on also. So you using this, so whatever I have got, so this particular orthogonality property I just want to use. So we use that by hitting on both sides. So as I said, multiplying on both sides and do whatever you feel like. See, ultimately, so we are actually going through the experience of Fourier while doing all this. So because in mathematics we will not allow otherwise, right? So right side is a infinite sum, and then you're just not going to multiply and say, okay, if I am going to multiply with one particular function, it's not going to multiply pointwise. We don't even know. All those things are just ignored for the time being. Okay, so we just wanted to do this. So that is how you got Cn to be equal to Cn to be equal to 1 over 2 pi times integral minus pi to plus pi f of x e to the minus inx dx. Okay, this is basically due to Fourier. This idea is completely going back and forth. Okay. Seem to be having problem. Okay, so uh, so your Cn is calculated now. So once you have the Cn, now you have some idea. Okay, this is how my series is going to look, and is there a possibility for me to think about whether this is just going to be convergent at all? So the convergence part comes only when you have the complete picture of the Fourier series. So okay, so your Fourier series is going to be given by, so it is going to be f of x, okay, approximately equal to summation n in z f hat n e to the in x, where f hat n is actually equal to 1 over 2 pi integral minus pi to plus pi f of x e to the minus in x dx, where n in z. Okay, so now as a simple example, I'm just going to do one of the problems. So f of x equal to x, you take this particular function, and then it is a function. Again, we have to, this is a function, if you are going to look up without any condition, okay, without having any condition like this, okay, so the condition that I have got, so this particular condition, if I don't have it, then this is a function defined only, defined on the whole of R, right? But I want a 2 pi periodic function. So that is the reason why I'm chopping it off in between. So I just needed a symmetric interval. And so I'm just chopping it off between minus pi and plus pi. And I'm looking at this particular function. Now, if this is a periodic function, means what? I'm going to extend this particular function as, as it is going to be on the entire real line. Okay, so on the entire real line, it is just going to look like only f of x equal to x as it looks in the interval minus pi to plus pi. Okay, so from minus pi to plus pi, it is equal to f of x, it is equal to x, and then from pi to 2 pi, it is again going to be f of x equal to x. So which means that you're going to get a kind of brush, okay, which is slanted on one side, right? Isn't that correct? So this is the kind of a function that you are looking at. And so the Fourier series, now you can calculate the Fourier series for this. Okay. This is basically, I don't have to explain so much because this is just going to come out through integration by parts. So you have f hat n to be equal to, when n is not equal to 0, f hat n to be equal to minus 1 over in minus 1 whole to the n not equal to 0. So you can always calculate by yourself now, just within the few minutes time that you have got. So this is just going to be exactly that. Okay, right? So your f hat n is actually going to be given by minus 1 whole to the n plus 1 over in n not equal to 0. Okay, but how about f hat of 0? Because I have calculated f hat n only when n not equal to 0. So how about f hat of 0? This is just going to be 1 over 2 pi integral minus pi to plus pi x dx. But x is a odd function and this is a symmetric interval. So it's just going to give you 0, the integral. Okay. So therefore, the Fourier series of f is just going to be given by, okay, f of x to be equal to summation minus infinity to plus infinity for n not equal to 0, because at n equal to 0, this is anyway 0. That is what we have found. F hat of 0 is 0. So for n not equal to 0, this sum is just going to run from minus infinity to plus infinity, minus 1 whole to the n plus 1 over in e to the inx. So if I'm just trying to now change it into, so I would rather just take it from the summation to be from 1 to infinity, using the relations that e to the inx minus e to the minus inx over 2I to be equal to sine nx. So then that is going to give you 2 times minus 1 to some 2 times summation 1 to infinity minus 1 whole to the power of n plus 1 over n sine nx. Okay, fine. Are you able to verify that this is correct or not? At least one of you? Are you able to check that? I just wanted to know one response at least.
Yes, ma'am.
Yeah. Okay. So you will have, so here what is happening, so notice that your f of x equal to x is an odd function, right? So the odd function is basically going to give you, okay, a Fourier series consisting of only sine terms. Okay, keep that in mind. And now let's consider f of x equal to x squared. Well, this is an even function, remember. Again, you want to have a periodic function, and so that is the reason why you are just going to have f of x equal to x squared minus pi less than or equal to x less than or equal to plus pi. Then the nth Fourier coefficient of f is given by, when n is not equal to 0, and I am going to use again the integration by parts method, and so that is going to give me f hat n to be equal to 2 times minus 1 whole to the n over n squared, okay, when n not equal to 0, and f hat of 0 equal to 1 over 2 pi integral minus pi to plus pi x squared dx, which is just going to give you pi squared over 3. Okay. And so the Fourier series of f is just going to be given by f of x equal to pi squared over 3 plus summation minus infinity to plus infinity 2 times minus 1 whole to the power of n over n squared e to the inx. But then this is also the same as pi squared over 3 plus summation 4 times minus 1 whole to the n over n squared, because again I'm going to use the relationship e to the inx plus e to the minus inx over 2 to equal to cos nx, and then for cos and sin nx you have some other relation, so I'm using that same thing. Okay, and so what you would get only the cost terms here. You're going to get only cost terms. Okay. The other ones are going to vanish for you. Okay. Okay. So we are just, so we wanted to try and see. We looked at an odd function and we looked at an even function. Okay. By the way, I just wanted you to do one simple calculation. I'll give you 5 minutes. Okay. What if I'm just going to take f of x equal to sine nx? Sine x, not even sine x, sine nx. You take f of x equal to sine x. What will be the Fourier series for that? Can you just calculate? Just we have done now.
I'm sorry, f of x equal to sine nx.
Yeah, f of x
Okay.
equal to sine x. So I'm just writing down
Okay.
f of x equal to here. F of x equal to sine x. So that is the one. Okay. Calculate and see what is the Fourier series for this.
I e power ix minus 1 by 2 I e power minus ix.
What was that? 1 over 2 pi?
1 by 2 I into
Yeah.
e power ix minus 1 by 2 I into e power minus ix.
Okay, so I mean, do you want to use the relation between e to the ix and sine nx, sine x? So what do you get? So actually, this is just going to give you, I mean, so you have to use the fact that sine x times sine nx, if n is not equal to 1, is 0. The integral of it is going to be 0. Sine x times cos nx, okay, whatever n may be, the integral from minus pi to plus pi is also going to be 0. Isn't that correct? And then f hat of 0 is going to be 0 anyway, because sine x is an odd function and the interval is symmetric, minus pi to plus pi. Correct? So what is going to be left out for you? Did you understand whatever I said just now? Or should I repeat it?
I understood, but I don't know how to prove the statement you said. But I
No,
understood the
no,
statement.
no. See what I've already given you the hint, right? So you want to try and find out. Okay, you want to try and calculate f hat n, right? Isn't that correct?
Yes, ma'am.
Yeah. So f hat n, you can always. I mean, so as I said, for the time being, when you are doing all these calculations, just forget about all the mathematical rigor. Okay, so you can write your f hat n to be equal to sine x. So here I'm looking at this particular formula. So sine x you have, instead of x I have sine x and e to the minus in x dx. Okay, but e to the minus in x I can write it as cos n x minus I times sine n x. Correct? Is it?
Yes, ma'am.
So now if n equal to 0, okay, I will have sine x dx integral minus pi to plus pi, and this is multiplied by 1 over 2 pi. Correct?
Yes, ma'am.
So this will give me 0 because sine x is an odd function. Right? Sine x is an odd function and my interval is minus pi to plus pi. The integral of a odd function on a symmetric interval,
Yes, ma'am.
will it be 0 or not?
It is 0.
So f hat of 0 is 0.
Yes, ma'am.
Okay, for n not equal to 0. Now n not equal to 0, you're looking at f hat n, that is equal to 1 over 2 pi integral minus pi to plus pi sine x times e to the minus in x dx. But then you write your e to the minus in x dx to e to the minus in x as cos n x minus I times sine n x. Correct?
Yes, ma'am.
Okay. Now your n is not equal to 0. Remember. Okay. And use the fact that sine x times cos n x, whatever n may be. Okay. N not equal to 0. For whatever n may be, sin x times cos n x integral is 0. This is something that you have done in your intermediate or whatever. I don't know whether you remember it or not. It will be 0. Okay. And don't try to calculate this now. I mean, so you want to verify it, whatever I am saying, you can do it after the class. Definitely you can do it after the class, but then take it on the face value that sin x times cos n x dx integral minus pi to plus pi is always going to be 0. Okay, as long as n not equal to 0. Okay, and the
Okay, ma'am.
next and the next one is sin x times sin n x dx integral minus pi to plus pi is always going to be 0 when n not equal to 1. Again, this is something that you can verify for yourself. Okay, later on, not now. Take it on the face value. So I'm only asking you to calculate what happens when n equal to 1. Okay, that is f hat at 1. F hat at 1 is 1 over 2 pi integral minus pi to plus pi sine square x dx. Correct? Because when n equal to 1, we already said that sine x times cos x dx is always going to be 0. So you ignore that part and then you have a I times whatever. Right? Maybe it is easier if I'm just going to say that sin x, you write it as e to the ix minus e to the minus ix over 2I. That may be easier for you. Substitute that and then calculate. That is much easier, much faster. What happened?
I think I understood, ma'am.
So it is just going to give you only sin x. Okay.
Yeah.
That is the only term that will survive. Okay. So the Fourier series for sin x is sin x itself. No other term survives. And similarly, if you take any other trigonometric function or any other trigonometric polynomial, then the Fourier series of the trigonometric polynomial is itself. Okay. So if you're going to take cos x, you will have the same kind of calculation and then you will get only cos x term surviving. And then you also have got similarly for any trigonometric polynomial, only that polynomial survives. Nothing else would be there. Okay. Okay, so keeping that in mind, so we wanted to try and see, suppose say, so you're writing down your Fourier series to be equal to, so f of x is approximately equal to integral, summation minus infinity to plus infinity f hat n e to the in x, and this is actually equal to f hat of 0 plus 1 to infinity f hat at evaluated at minus n times e to the minus in x plus summation 1 to infinity f hat n e to the in x, and this is actually equal to f hat at 0 plus summation 1 to infinity f hat minus n plus f hat n cos n x plus I times, okay, why am I getting this I? That is because I'm just using this particular thing. So I'm using the relationship between the e to the in x and cos n x and e to the in x and sin n x. So I'm just using those relations. Okay. And so that is how I got this particular expression. Okay. This is the expression that I'm getting only from the relation that I have got here. Okay. So I would get this kind of an expression. And now if my f is just going to be even function, so that is f of x equal to f of minus x equal to f of x, then you can easily calculate by the formula and show that f hat of minus n is actually equal to f hat n. Okay, it will just come out to be that. And similarly, if f is odd, that is f of minus x equal to minus of f of x, then f hat at minus n is going to give you minus f hat n. Okay, so with these two relationships, whatever I have told, so if f is okay, so sure, f is even, so f hat will also be even. That means that, so I'm just going to add here f hat at minus n is actually equal to f hat n, and that is, so f hat of minus n is actually equal to minus f hat n. This is a simple calculation with a small little change of variable that you can always evaluate. Okay, that will give you that. So if f is even, then what will happen? So if f is even, your so if f is even, this particular thing is going to vanish, right? Because it turns out to be f hat n minus f hat n. Because f hat at minus n is actually equal to f hat n, right? That's what I said. Isn't that correct?
Yes, ma'am.
So you're going to have this particular term is going to vanish, and so you will have only this bit in the Fourier series that survives. Okay, and if f is going to be r, then what will happen? So if f is going to be r, then this particular portion is going to give you minus f hat n, and so cosine terms will vanish completely, and you will have, okay, that f hat 0 will also be 0. That is because of some other thing, yeah, because it's an odd function, and so the integral is just going to give you 0. Okay, that will go away, and this is the only thing which is just going to survive. Okay, so you will have, if f is even, that is why I said f of x is actually equal to f at 0 plus 2 times summation 1 to infinity f hat n cos n x, and when f is odd, then f of x equal to approximately equal to 2i times summation f hat n sin n x. Okay, so this is what it is going to come out to be. Okay, now well, whatever I'm aiming at is to try and show that, uh, remember, we have discussed Banach-Steinhaus principle. So this Banach-Steinhaus principle, I told you that it is just going to give you something. What is that something? That it proves that there is a function for which its Fourier series diverges at each and every point. Okay, it doesn't converge at all to the function. It diverges in almost every point. Okay, that's what we wanted to try and show, and so we want to try and see what is that. I mean, we are really coming to this particular point where, uh, after I discuss the Dirichlet kernel, actually, I'm just going to prove that particular fact for you, that you have a function whose Fourier series diverges at each and every point using the Banach-Steinhaus principle. Okay, we'll see that. So okay, so here is Dirichlet kernel. What is this Dirichlet kernel? So we know. So okay, so there's one more thing which I wanted to say is that Fourier series is actually really very special. Okay, very special in the sense that, the convergence, if at all it converges so beautifully. Like, I mean, it converges really very nicely. Okay, that okay. So here is something that I wanted to share. 1 second. I'm going to. I will have. I don't know whether I can share two of them, or maybe I will do this. Yeah, I'll just stop this first. Oops. 1 second. I want to bring in and show you the other one as well. Give me 1 minute. I'm just coming. Okay. So, okay. Let me see if I can share this on the screen. don't know whether I can share this screen. Let me see. Yeah. Can you see that now?
Yes, ma'am.
Yeah. So this is the way. So this is the, see, the uh, the graph of x squared, right? So if you look at the second partial sum for x squared from the Fourier series, this is how it looks. Okay, and with 4 terms, the graph of this is going to give you like this. Okay, and for 6 terms, you see, it's almost really coming out to be the exact one. But with 6 terms, it is coming out to be this, and then for 8 terms, it is exactly equal to that. See, I mean, this is the best thing about Fourier series. So it is not just only with the functions, it can actually approximate whatever kind of function that you look at. Okay, so even if you have got the face of a human being, the Fourier series, if you, once you calculate for this particular function, the Fourier series actually approximates it so well. Okay, and within a few terms, actually it converges to the face of the human being. I'll show you the video next time in the next class, or maybe whenever I come to the class once again, in the offline class, I'll show you that. It will be very nice to watch actually. Okay, and so I'm just stopping this sharing, so we're going to go back. Okay, I have to go back to this 1 second. Coming back. Right. So did you get it? Can you see my screen? Yeah. Okay. Okay. So what's the Dirichlet kernel? So we know that now we have calculated the Fourier series for a few functions, and so we want to try and see, okay, what about the convergence now? Okay, we want to discuss about it. So in that process, we will have to actually look at this particular thing, what is called a Dirichlet kernel. So we know that if the sequence of the partial sums for the formal Fourier series converges, then it can represent a function. Right? This is something that we know. We already know this. The only if you have, so now comes the mathematics. All okay. So now consider the symmetric partial sum Sn of x equal to summation minus n to plus n f hat n e to the I n x. Okay. So this can be written in the form Sn of f of x equal to 1 over 2 pi integral minus pi to plus pi f of y dn x minus y dy. Okay, so I have to calculate what this dn is now. Okay, so where the function dn called the Dirichlet kernel given by dn of x equal to summation minus n to plus n e to the I n x. So why is that it is going to be like this? We'll have to see. Why is that? It's because, so I have f hat n, so I'm writing down f hat n. So let's look at this. I have written the formula for f hat n. Okay. So what is f hat n? F hat n is integral minus pi to plus pi 1 over 2 pi f of y e to the minus ixy dy. Correct? Isn't that correct? So should I write it down? So this is the same as, so I'm just writing down. It's the same as, okay, minus n to plus n 1 over 2 pi integral minus pi to plus pi f of x, okay, e to the minus I n x, correct? Yeah, Okay, so this x and that x should not be the same, so I have to change because the x is a dummy variable in the integral. So let me write down that 1 over 2 pi integral minus pi to plus pi f of y e to the minus I n y dy, and now this is multiplied with e to the plus I n x, right? That is all that I have got out here. Yeah. So from this, you can always see this is what it would come out to be, right? This is the end result. Isn't that correct? Yes or no? Is that correct? Are you people there?
Yes, ma'am.
Can you hear me?
Yeah, yes, ma'am.
And so what you get is only this right hand side expression. This is the expression that you would get right from here. Correct? Isn't that right or not? This is the expression that you would get from here. And so you would take dn to be equal to summation minus n to plus n e to the I n x. Okay? And now you want to try and show a compact form for this dn of x. Okay? So for that, you are going to write, so you want to really try and write down a compact form. What is the compact form? This is the compact form that I am trying to look at. Okay? Fine? Right? So how do I write it? So dn of x equal to summation minus n to plus n e to the I n x, and this is actually equal to, I'm just going to split it up as three parts, minus n to minus 1, and then plus 1 to n, and then you have plus 1, because for n equal to 0 you will have e to the 0, and this is just going to give you 1, right? This is the only thing. So these are the parts that are very clear for you, correct? So now okay, so from here I'm going to add and subtract 1 so that I can write down these summations from 0 to 1. Okay, so that is just going to give you, see, this 1 together with this is going to give you this, right? And then if I add one more 1, then I can get from here this particular thing. Okay, but then because I have added 1, so I have to subtract 1, so that is why I have a minus 1. Okay, so this is just going to give me minus 1 times summation 0 to n e to the minus I n x plus summation 0 to n e to the I n x, and then that is actually equal to minus 1 plus summation 0 to n e to the minus I x whole to the n plus summation 0 to n e to the I x whole to the n. So now you put w equal to e to the ix, then we will have dnx to be equal to minus 1 plus w to the minus n summation 0 to n, and then summation 0 to n w to the n. So this you sum it up using these formulas that you know already, and you are going to get, okay, so the simplification is going to be left out for you. So it will give you this, okay, minus 1 plus w minus w to the minus n by w minus n plus 1 minus w to the n plus 1 by 1 minus w, and this is just going to give me w to the minus n minus w to the n plus 1 over 1 minus w. So remember, this is a w minus 1 in the denominator here, and this is a 1 minus w, because if I'm just going to take this 1 minus w as the common denominator, that is going to give me a negative sign for the numerator. Okay, so that is how you're going to get this. Fine. Now I will multiply and divide by w to the minus half, which I can do because it is e to the ix. W is e to the ix, and so I can always multiply and divide by w to the minus half out here for this expression. Okay, which I am going to do, and I will give you that will give you w to the minus n minus half minus w to the n plus half, and that over w to the minus half minus w to the half. So w to the half, now you replace w with e to the ix, and I will get exactly the same expression. Okay, right? Okay, but notice that your dn is just only a trigonometric polynomial, right? This is just trigonometric polynomial, exactly a trigonometric polynomial. So if I'm just going to write down the Fourier series for this, it will give me exactly the same thing again. Okay, so which means that the Fourier coefficients, so the Fourier coefficients of dn are given by dn hat of n equal to 1 if mod n is less than or equal to n, and it is equal to 0 otherwise. Correct? Isn't that right? Yes or no? Are you there?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Okay. So it will be giving you only this, right? It is exactly the same thing. The Fourier series is actually going to be only that, only itself. And so naturally, dn hat evaluated at n equal to 1 if mod n less than or equal to capital N, and it is equal to 0 otherwise. Okay? Okay, let's leave it at this point, and so I'm going to stop here because one thing is that I cannot sit for too long. Okay, and in the next class I'm going to use this particular thing. Okay, another thing is that, okay, there's one more thing. What if I'm so can we integrate this out? Okay, so I'll show you. I mean, this is actually the integral of this particular function. Integral of mod dn is going to be infinite. That is something that is, I mean, that it tends to infinity actually as n goes to infinity. That is something that you can see very easily, right? I'm saying mod dn. What will happen to the mod dn then? Okay, let me share something here. Uh, I'll show you what the graph of this particular function is going to look like. Oh, what happened? Oh, it got stuck. 1 second. I don't know what happened to this. Okay. Wow. I'm sorry, 1 second. Because it was stuck. Somehow it was just getting stuck. Okay. Okay. So can you see? Can you see my screen?
Yes, ma'am.
Yeah. So see, D2 looks like this. D4 looks like this. And so one more I'll show you. So this is just going to be stop the share and then this one. Okay. Okay. Can you see that? This thing is obstructing your view. Yeah. So as you increase, so D6 looks like this and D8 looks like this. So if you're going to integrate this out, integrate this particular Dirichlet kernel, actually it is just going to give you infinity. As so if you take the integral dn, okay, as n goes to infinity, this will see whatever you are seeing out here is just not going to be, and so the see it keeps on spreading out, never dies out. So the integral when you calculate is always going to add up something at whatever n may be. So it keeps on adding. So naturally the integral is not going to be finite for this particular function. Correct? If you take n going to infinity, it keeps on increasing. See so for integral d8, whatever, if you take integral of d8, it will be less than integral of d10, definitely. And so it keeps on increasing. The value of the integral keeps on increasing, and it never stops anywhere. Okay, so the integral dn as n goes to infinity is going to tend to infinity. Okay, this is a crucial fact which we will be using in the next class to prove that the Fourier series, I mean, there is a function whose Fourier series would always diverge. Okay, keep that in mind, and then I'll stop the class now. Okay, thank you for joining me, and then agreeing to listen.